Perfect. So welcome to Exploring Machine Learning Libraries workshop. It's hosted by the Data Science Committee of Baruch CIS. And the agenda for today's session is we're gonna look at 3 libraries. So we're gonna look at the very cool library called Scikit-Learn. Specifically, what we're gonna do is only supervised learning because it's very explanatory and more transparent than unsupervised learning. Then we're gonna look at lazy predict. I'm not sure if you remember, but it kind of got a lot of attention when it was first published because it can iterate over like each model within like the classification and regression and like tell you the various performance measures of that model for this particular data set. So this will be the second library, and afterwards, the third part, we're gonna take a sneak peek into deep learning. So we're gonna discuss TensorFlow, specifically the Keras API. Yeah, but we're not gonna go too in depth. So we're just gonna do a quick example for you to see that it's actually not intimidating, and yeah. Cool. So let's start with Scikit-Learn. First of all, this is the documentation, and it has a lot of components to it. For example, for every data science workshop, we usually deal with data sets. And for during the last workshop, I actually asked people to like download the data sets prior to the workshop. But today we're not gonna do that because today we're just gonna import the data sets from Scikit-Learn because they provide it to us, which is awesome. It's very helpful. So what you can do with Scikit-Learn is classification and regression. I'm assuming most of you have taken CIS 2300. Yeah. Is there anyone who didn't take this course? You can like raise your hand or go off mute.
Me?
Okay. Yeah. You did not take this course? Okay, perfect. That's fine. So Python is a scripting language, but Python is also like an object-oriented language, like programming language. So we like anything that we do and like anything like that we get in Python, we can store it as a variable. So here we're dealing with a data set. So we're gonna store the data set, and like even after we split it up, we're gonna store the components in variables, right? And when we instantiate the models, we're also gonna store them in variables, which is very convenient because variables are awesome, and also different libraries allow us to do different methods on variables. So it's very convenient, I think. It makes it very compact. So usually, let me just skip to one line of code. So let's say we have this, right? So in this case, the variable will be x, and we assign this object, which is, it's like the columns of a data set without the target column. So we assign this data set, which is in form of a matrix, to this variable called x. And then we're gonna use it afterwards. So we would not need to like repeat. We would not need to write this whole thing instead of x. We can just put x. Yeah. This is the logic behind it. Cool. So let's get started with Scikit-Learn. First, let's get the data. Yeah. We will be getting, for like the classification with k nearest neighbors, we will be getting the wine dataset, the wine recognition dataset, which basically it's a data set that contains features and targets. Yeah, Daria, do you want to tell us what the target variable should be in classification?
Yeah, so basically the classification, we're trying to determine the target variable. For this, there's going to be 3 target variables. It's trying to determine if it's either a wine is class 0, 1, or 2. Later, we'll also be doing regressions, and regression, it's going to try and predict the target variable.
Yeah, so we're trying to predict the target variable regardless, but with classification, the target variable has a limited number of options. So in this case, we have a column that consists only of the values class 0, class 1, and class 2. But with regression that we're gonna talk about later, we are trying to predict a continuous value. So there is no limitations of the values that are in the target variable, except the range, but it's still it's continuous. Okay, so we're loading the wine dataset right now using the datasets module and the load wine function, and we're gonna store it in a variable called wine, right? When we print the description, let's do it right now. It's gonna show us, okay, so these are the features. The features are basically in a dataset, all columns except the target variable, which is the target column. So I think we have 13 columns, something like that. And we also have descriptive statistics for each of the columns. So attributes of wine are alcohol, malic acid, ash, alkalinity of ash, and so on. Yeah. So yeah, and the rows usually look like this. So it's not stored in a table, although we could store it in a table. And usually when you're doing a project that has some sort of machine learning, you would want to use pandas instead of NumPy, or instead of just arrays, because you're gonna have to complete lots of exploratory data analysis and data cleaning and data sanity checks before you feed the data into the model. But right now, our data set is perfect as is. It is, yeah, it doesn't have any missing values. I don't think Scikit-Learn can even deal with missing values. But yeah. So yeah, and once again, as Daria mentioned, these are the target's names. Yeah, so we have the target column, and these are all the values that can be in this column. Cool. Now we know what our dataset looks like. Let's import the actual model from Scikit-Learn. And what we're also going to import is this module, which is train test split. And why would we need to do that? Does anyone know? Why would we need to take the whole data set and split it into training and testing? Okay, that's fine. So the key idea behind it is that when we are building the model, we are training it on the training set, and we leave the test set alone for this process. But after the model is built, so it's trained on this training dataset, we have to evaluate its performance somehow. But we can't do that if we don't have data. So we gotta set a piece aside to then test the model on the test set and see what the accuracy is with the case of classification, or what the error is when we move on to regression. But yeah, so once again, we store the feature values in X. So like all of the columns that you saw here, these ones are going to be stored in X. And the target, which contains these target names, is going to be stored in Y. So, and this is the syntax that's you're going to see everywhere when you try to split the data set. So you create those 4 variables, xtrain, xtest, ytrain, and ytest, and you assign it the output of this function, train test split, and it takes the following arguments. It takes the features, x, and the targets column, y, and it also, you should also specify the size of the test set. Yeah, usually, well, sometimes you can see like 30%, sometimes you can see 20%. I'm doing 30% for the test size in this case. Random state is just for replicability, so we get the same value here. And one really important concept, something that we really should pay attention to, is that we want our test set to be representative of the distribution of like observations per class. So we have 3 classes, 0, 1, and 2. And the number of observations in class 0 are 59. In class 1, there are 71 observations and 48 observations in class 2. So we need the same distribution in the test set as well, because when we measure for performance, we're trying to like mimic the real world, basically. Like what happens if you know, we don't know the labels, right? So we add this argument. We add stratify y. Cool. Now that we have created those subsets, we're gonna create the KNN classifier with 7 n neighbors. What it's gonna do, it's gonna basically group the observations together. Yeah, and this parameter, n neighbors, basically you can think about it this way: as this number increases, the decision boundary, so like the kind of the boundary of the clusters, they become smoother, and hence the model becomes simpler, and the model can be the model becomes less sensitive to noise, right? However, if the k is a really high number, then yeah, there's a chance that the model is going to underfit the data. And what is the difference between overfitting and underfitting? Daria, do you want to answer this?
Yeah, so just to put into simple terms, it's like overfitting, it's too specific for the model, and underfitting, it's like it's not specific enough. So when you're going to be testing it, it's like you want something right in the middle so it can kind of be generalized later on.
Yeah, perfect. Also, good keyword, we need the model to generalize well on new data. So the data that the model hasn't seen before, right? Otherwise, the model will be useless. So we really need the model to be able to generalize well. So yeah, after we instantiate the model with the parameters that we need, we store the model in this variable called KNN. And what's left is the training. So yeah, we're gonna do the fit method on KNN, like on the model. And we're gonna the fit basically refers to like training. So you're gonna train the model on xtrain and ytrain, right? And after the model is trained here, it's gonna we would want to print the accuracy. Yeah, we would want to print the accuracy, and we can do this by calling the score method on KNN also, because the model is stored in KNN. And we're going to call the score method, and those will be the arguments. So X-test and Y-test. Because, once again, we train the model on the training set, but we want to evaluate the model on the test set. Yeah. Okay, and we get the accuracy of 74%. It's not like the best accuracy ever. I think the best accuracy is like 100%, which you'll never, I think you'll never get to see that, but yeah, this is pretty decent, I think. Okay, now I want to just quickly talk about how we figure out what the n neighbors argument should be. Like, what should be this number, right? Well, there probably are some functions to determine it, but you could just, like, a simple answer to this is you will just iterate over the values of k. Like, you specify the minimum value that k can be, in this case 1, right? Because we're trying to group the observations together. The minimum value would be the integer 1. And let's say we don't want to group more than 10 observations together, right? So we're gonna first import these modules, which we're gonna use later. Yeah, NumPy just creates sequences for you and arrays. And matplotlib is a data visualization tool. So right now with NumPy, we create a range of, or like a sequence from 1 to 10. Like, it's a sequence of integers. And we will use it to like iterate over each value of the n neighbors, right? Then we're gonna create empty empty objects of train accuracy and test accuracy. Yeah, cool. And then we're just gonna write a simple for loop. So for those who have not taken CIS 2300, the for loop is basically the simplest way to like automate things. What you could do is you could manually substitute the numbers of k into the model, but it's gonna be a little bit tedious. And like, where are you gonna store the results, right? So we're just gonna write a for loop that makes it for us. Cool. Yeah, once again, it's the same process. So we instantiate the model, the same model that we did here. However, we don't split like hard code the k variable. So yeah, we don't like write here 7. We write k because in each iteration k changes. So we instantiate the model, then we train the model, like exact same step as here. And then we're just gonna store the accuracy. Once again, the accuracy can be, it's like the score method, right? We're gonna store the accuracy of the model on the training data. And we're gonna store the accuracy of the model on the test data in those objects, right? And it's gonna store, with the for loop, it's gonna store all the accuracy scores for k from 1 to 10. Yeah, so after we plot it, this is just a code to visualize it. We can see this. So the y-axis is accuracy, the x-axis is the number of neighbors. So as the number of neighbors increases, as k increases, right, the training accuracy tends to decline, but that's okay. What we care about is the testing accuracy. So yeah, at what number of k is the accuracy the highest? like I can see that at at k equals to 5 and k equals to 7, those are kind of the peaks. So I want to say that 7 would be the appropriate k to use in this particular case. So this is how we find k. Okay, perfect. Yeah, but also I want to mention that there are other performance measures besides accuracy. So right now, we just did a fun example with like the categories of wine. But if you have like a fraud detection system and you want to measure how the performance works, you would not use accuracy. You will use those. Like you definitely would use the confusion matrix. And with fraud detection, you want to minimize the false negative value, which is the top right one. Like you're gonna get a matrix 2 by 2, and you want to minimize the top right value, which is called the false positive. There's also these other metrics. So precision, also recall, which is the sensitivity. I personally like this one, F-score. It tells you a lot, and specificity. So you would need to determine which metric you are going to use before you even get started on your project. You're going to have to determine it based on the business problem. All right, and yeah, this is just an example of how we can. We already like trained the model, and we also measured the accuracy. But what's left is predicting. We can also predict the target variable based on new data that does not contain the labels. By the way, the labels are the values of the targets column. So the labels in this case would be this. Yeah, there are 3 unique labels: class 0, class 1, and class 2. Okay, so let's say we go to the supermarket and we find, like, we want to decide between 2 bottles of wine. And ideally, like, the higher the class, the better. But we're not being told the class. We're being told all these other attributes, which is like, I think alcohol percentage, magnesium, ash, and so on. Like 13 data points. And we have all of these data points for one bottle and for another. So yeah, let's try plugging them into our model and predicting new values, like predicting the label based on this new data. So first of all, we store this new data in XNew, and then we do this. So we call the predict method. The parameter, like the argument, is XNew. So these new data, like data points, 2 data points. And we're gonna still have to use our model, which we defined previously. And we're gonna store the output in this variable called new prediction. And then when we print it out, it's gonna tell us that the first bottle, like the bottle with these attributes, is of class 0, and the bottle with these attributes is of class 2. So we're gonna go with bottle number 2. Cool. I think we are done with classification for now. Does anyone have any questions? Is there anything I should explain in more detail? Any processes? Okay. If you have any questions, just hop off mute, raise your hand, or you can send them in the chat. Yeah. My data science associates regularly check the chat, right? Yeah, perfect. So let's move on to regression. Here we're trying to predict a continuous value. So not a class, like a number, right? So with regression, In simple terms, you can think of it as like this linear equation, right? We have the independent variable and we have the dependent variable, right? And the independent variable causes the dependent variable. So in this case, x causes y. However, if we have like a data set and we have a bunch of these values, x and y, the question is, how would we like choose the coefficients? How would we estimate them? Well, machine learning can help us with this task. So once again, let's load a dataset, but this time a different dataset that has a different target column. Yeah. Okay. We are gonna load from Scikit-Learn, like using Scikit-Learn's API. We're gonna load the California housing dataset. Cool. And when we print it, it's gonna tell us that those are the features, which is in this case x, like the independent variable, right? We have median income in a block group in California. We have the median house age in a block, also in a block group, the average number of rooms, the average bedrooms, the population, average occupation. Yeah. Oh no. Average occupancy. Yeah. The average number of household members. The latitude and longitude. And what are we trying to predict? We're trying to predict the median house value in each block based on all those features, right? Ideally, when you have a data set and you have features, what you could do before plugging them into a model is you can do feature extraction, which is just basically creating new columns from existing ones. So for example, you could create a column that calculates the average bedroom to room ratio. So it takes the value of bedrooms and divides it by the number of rooms. You get a new column. And yeah, sometimes, so why we do this, right? With regression, sometimes the like extracted features are actually like they cause the dependent variable more, if that makes sense. So we're trying to obviously do that. Yeah. Okay. So for now, let's see that. So I think that median income is like causes the median house value the most. So like when people in a block tend to earn more, I would think that the median house value also goes up. But right now it's just a hypothesis. Yeah. So let's take this this column and we're gonna store it in this variable. Yeah. And we also need the target column. And then we're gonna use these to plug into our model, basically. So once again, we import modules. And here, you've seen this before in classification. We also use it in regression. We do the train test split on x, which is median income, the independent variable, and median house value, which is the dependent variable, y. We also specify the test size, but the key difference is that here we do not have the parameter stratify because we don't know what the population looks like. Yeah. Yeah, and once again, the same steps. So we're gonna instantiate the model. So you can see this in line 11. We instantiate the linear regression model. here we imported it, and here we like create it, and we store it in the variable regall. We also, well, then we're going to train the model on the training data set, which is the exact same syntax. So it's going to do, we're going to do a fit method, and the arguments are xtrain and ytrain. And after we build our model and train it on the training data set, we would want to predict make a prediction on new values that the model hasn't seen before. And the model hasn't seen x-test values before. So it's just a portion of the median income that was not used when we were training the model. So let's store our predictions here in this variable, y prime. Yeah. And what are we gonna do after we make the prediction? We want to evaluate the model, obviously, but here we have different metrics. So with classification, we had accuracy, we had the F-score, confusion matrix, right? All of that. But the performance measure, like the metrics, are different here because because right now we're trying. Oh, no, wrong. Okay. Right now we're trying to predict it, like get the error basically. Yeah. We measure the performance of our model in the error of, like, in a difference between what value we predicted and what value there was actually. So the y-tests are the values that actually happen, and the y-prime is our prediction. So yeah, we're trying to measure like how far away we got from the actual values. And yeah, some of the measures are r-squared and the root mean squared error. Yeah, let's visualize it. I'm gonna explain what that means. So for our housing data set, we have the independent variable here, which is the median income per log, and we have the median house value, which this is the values that we're trying to predict, and it's continuous. So we're not trying to predict a specific class, trying just to predict the value, right? So the black line is sorry. The black line is our, like, this linear equation, right? It's our model that has already the estimated coefficients. Yeah. And everything on the model is the predicted values. However, yeah, if we try to test the model based on like median income and it's 6, and we predicted right here, which is around 3, but the actual value is like this here, like above the line, around 5, then we're trying to measure the distance. Yeah, the distance between this point and this line. And this will be our error. Cool. Yeah, and this is just us visualizing how we're doing. So as you can see, as the median income tends to increase, the median house value also tends to increase. So yeah, and it's kind of a linear, it's kind of a linear trend. Or at least there is the linear trend for this specific data set. Okay, and oh, no, wait. So usually you would use regularization to avoid like for regression specifically, you want to avoid the coefficients being too high, like too big, because this can lead to overfitting. So you would want to use regularization, and two ways to do this is lasso and ridge. So ridge actually helps like minimize, like it performs a loss function and it helps minimize the loss, but it also adds a penalty term if the absolute value for each coefficient is like too high. With the lasso, it assigns coefficients to features. So with this particular model, we only had one feature, which is the median income. It's the independent variable. However, when we're trying to predict like a value, median house value, on multiple features, so let's say median income, house age, population, something like that, like a combination of those three, or like maybe all of them, we can use lasso to actually assign the coefficient itself. And one thing about lasso is that it assigns the coefficient of 0 if the coefficient is like insignificant, so it doesn't really affect the target. Okay. The stats, are we good until now? Does anyone have any questions?
Actually, I have a quick question. You know how like when you have many independent variables, it can lead to like the multicollinearity, if I'm saying that right, where it's like it runs into the problem where the independent variables are like determine one another basically. Can this specific library determine that, or
what do you mean by they cause, like, you mean the features itself cause each other?
yeah, so it's like the independent variables, it's like it kind of causes a problem when determining determining why, like the two x's, for example, are kind of like are related to one another, so like one causes the other, and it causes like collinearity, like.
Oh, you mean like they are correlated?
Yeah.
Okay, perfect. Yeah, then yeah, then we could just again extract a feature. So for example, wait, let me go back to the thingies. Okay. So let's say wait, the average occupancy is determined by the population density in this particular block, right? And they are correlated. Like maybe there is a causation effect, maybe not, but they are correlated. What we can do is we can extract a feature from both of them. So we can create a new column, and then we can drop the two columns because they don't add any, like, we can drop them after we create the new feature, because we wouldn't want like two values that are correlated in a model, because there's not much like addition per feature. Yeah. So yeah, just do feature extraction and get rid of the previous features. Does that make sense?
Yeah, perfect. Thank you.
Okay, perfect. So let's move on to decision trees. Decision trees can do both classification and regression, but the classification is what we saw previously, but with regression, it's decision trees can do a non-linear regression. Yeah. So yeah, and let's explore this a little bit. So for classification, once again, we import a data set, but right now it's a new data set. So right now we're importing a digits data set, which just contains images of digits and the features that are associated with them. Yeah, and what we're trying to predict is based on the features, like what is the digit? So it is a classification problem. So once again, we assign the features to X and the target to Y. And we split the data set into training and testing. And here's our key parameter, stratify, right? Because we want to keep the distribution of the whole, let's say, data set or population in the test set as well. Yeah, and then we import this model called decision tree classifier, and also this metric, accuracy score. We used accuracy in the previous classification problem, and we're going to use it here as well. So we're going to instantiate this model that we imported, and we're going to pass on some parameters to it. So let's say, oh, by the way, does anyone know how decision trees look like? So yeah, these are these things. Basically, we have the root, which is just the training dataset, the whole thing, and then we basically put like a condition to it. It's more like, you can think about it like if else, right? If the condition is true, then we split the root into the leaf. Wait, the node, this node, and if the condition is false, then we're gonna split the root into the different node, and so on. It's like a bunch of if-else statements. Yeah. Cool. So we set the maximum depth, so the maximum number of the maximum number of nodes, like node layers. We set it to 6. Also, we set the criterion to Gini, and this basically means that we want to minimize the impurity of each node. So I'm trying. I'll try to explain it in like better English, I think. So the Gini index measures the impurity of each node. So when the Gini index, the maximum value that the Gini index can have is 0.5, because then the split, like the node, will contain the node will contain 50% of observations that have one label and 50% of observations that have a second label. So it's like very mixed. What we're trying to do is we're trying to get the Gini criterion, like with each layer. We're trying to get the Gini criterion, we're trying to decrease it, right? So we're trying to make each node contain more of one type of observations. Yeah, this is basically it. Here we instantiate it. And then again, we will follow the steps that we followed before. We instantiate it, we train the model, so we fit it on the training set, and then we can predict on the test set. So we will store the predictions in this variable, and we will predict on X test. And yeah, then we're just gonna measure the accuracy of our prediction. We call this metric, which we imported, accuracy score. And the parameters should be the actual labels, the actual values, and our prediction. And we're going to compare them. yeah, and right now the accuracy with the Gini index is 78%, which is, it's okay, it's decent. Cool. We can also use another index, which is entropy. It's very similar. It just, entropy measures the error, I think. Yeah. So the maximum value of entropy is 1. And yeah, once again, we're trying to minimize the entropy of each node. This is one node. This is like, the squares are the nodes. Okay. And the accuracy of the model using entropy is slightly higher, like by maybe 0.5%. Yeah. Cool. And this is this was the decision tree classifier. We can also do regression. This is very helpful when the regression is when the like the equation is nonlinear. So it's not going to be y equals ax plus b. It's going to be something else. So for this specific problem, I want to show you something. We're going to work on the same data set. We're going to work on California housing data set with the values that's basically with this. Yeah. Okay. Yeah, but this time we're gonna work with like all independent variables, not just one. Okay. Yeah, once again, we load the data set, we get the features, we get the targets column. We split the data set, the training and testing, using like the independent variables, which is features, and the target column, which we're trying to predict afterwards. The test size, here again, I'm using 30%. Yeah, and we import this model now. It's called decision tree regressor. Here it was decision tree classifier, but now we're using decision tree regressor. So this is how you can differentiate between those. And yeah, we're just gonna call the model. We're gonna specify those parameters. The max depth, you're already familiar with that. Like we're trying to limit the number of like, I guess, like layers the tree has. And we also specify that we, like in each leaf, which is the end node, right? These are the leaves on the bottom. In each leaf, we want no less than 13% of the training, like of the training observations, basically. So yeah. So it doesn't, it's less sensitive to noise, right? Because if like in an end leaf, if the minimum samples, if the samples are like 5% of the whole training set, yeah, it's gonna be like sensitive to noise too much. So yeah, so we instantiated this decision tree. Then we train on our model, on the training dataset. And yeah, once the model is built, we're gonna import the metrics. Right now we're using mean squared error, which is, I think the mean squared error is like, it's the absolute value of, yeah, it's the absolute value of the error. And R squared is the error expressed in percentages. Yeah. So right now we're gonna compute our predictions. We're gonna make the model predict on the on the test features, like test set features. And then we're gonna compare, we're gonna compute the metric. We're gonna see like what the mean squared error is. So just like with the accuracy, the parameters are always y-test and y-prad. So like the actual labels associate with like the observations that we're trying to predict the labels on, and our prediction. Okay, and yeah, now we have the mean squared error, and the metric that I discussed previously is root mean squared error. Yeah, this one. Yeah, we just yeah, so with root mean squared error, we just take the root of mean squared error. Yeah, because that's in the names. And the root mean squared error is 0.86. And let's see, so we used this model and the previous like regression model on the same data set. Let's compare the RMSE. So here it's 0.86. And right here is 0.83. Yeah. Okay. Cool. So that was it. So far with Scikit-Learn we covered classification, regression, and decision trees. Cool. All of this was supervised learning. So all the code actually made it transparent of what we do and like what the model does, because we specified the parameters. Unsupervised learning is more like a black box. So it really depends on the business problem, but supervised learning is like my preferred method. And let's move on to lazy predict, the library that got a lot of attention recently when it was posted. Does anyone know what the library is about? No? Well, when it was posted on I think I first saw it in an email subscription, but it was also posted on LinkedIn and it like gathered a lot of attention. So this is the GitHub from the author of the library. By the way, if you want to, you can create your own library. And I encourage you, yeah, let us know if you do, because we are very interested in this. Yeah, but this is the documentation, this is the GitHub. Yeah, and what it basically does, oh, by the way, we need to pip install it because we cannot import it otherwise. Yeah. Yeah, what LazyPredict does is it helps build a lot of basic models without much code or any parameter tuning, and evaluate the models for different metrics and execution time. And yeah, it can be also used with the Scikit-Learn API to load the data. So we import the LazyPredict, and then it also supports like the problem of classification and regression. So with classification, we import the lazy classifier, which is the LazyPredicts module. And from Scikit-Learn, we import the breast cancer dataset, which, wait, where is it? Oh yeah, it's a classification problem. So, yeah, and then again, the same steps, we're gonna first load the data into this variable called data. We're gonna assign the features to X and assign the target column to Y. And then we're gonna split it into training and testing, just as we did before. Then this is where the lazy classifier comes into play. So we instantiate this model with those parameters. Oh yeah, apparently you can do custom metrics, but you don't have to. And we assign, then we train the model on the training and testing, I guess. And we assign it, oh yeah, hold on. We train the model on training set, and we assign it to models. And then we also do the predictions at the same time in the same line. And we assign the predictions to the predictions variable, which is this. So we kind of, yeah, we kind of get two variables at the end. And when you call the models, which stores the model, yeah, which stores the models. These are all of the models that you see, right? So it's the linear, like it's the logistic regression, XGB classifier too. So, and for some reason, the decision tree classifier is right there on the bottom, and they're sorted based on their performance. So these guys do better than the ones on the bottom. And those are the metrics. So accuracy is measured, balance accuracy, also the ROC or ROC curve, which is another metric, the F score or F1 score, and the time it takes to build the model. I think it's pretty cool. I think it's like super useful for when you don't know like which model to use. Yeah, like it gives you like a starting point, right? When you already have the model, then you can like perform like hyperparameter tuning and all of that, but it's a good starting point. I think this library is awesome. And we can do the same thing for regression, right? This was lazy classifier, and here we have lazy regressor. We also import data sets. Yeah, this time it's for some reason it's, yeah, I'm not sure. Wait, it's low diabetes. Yeah. Cool. So below the diabetes dataset, it should be this variable should be diabetes, but whatever. Then we randomize it. We randomize the variables, and again we assign the data to X and the target variable to Y, and we convert the X to like the float data type. Yeah. And then we perform those manipulations. And we instantiate the lazy regressor with those parameters. Also, no custom metrics, and verbose equals 0. But yeah, after you have picked your model, you can create your own metrics, and like, you can change the hyperparameters and add some. And yeah, almost the same syntax as previously. And once again, we iterate over each of these models and we measure them for different metrics. So it's adjusted R-squared, RMSE, and the time taken. Okay. Yeah. This was Lazy Predict. How are you feeling about this library?
Why was it so controversial when it came out?
Was it?
Oh, I thought you said it was like controversial when it came out. Like,
Oh no, it got a lot of attention. No.
Oh.
Yeah. It was, people were like, oh, this is cool, this is cool. So
would you use it like before you do the like regression or like a specific model, or do you want to do the regression and then see what model works best for data set?
So there's this assumption that's called no free lunches. And it's basically about if we didn't make assumptions about the data, then we would use, we could use any model, right? However, this is not the case because we always make assumptions about data. So yeah, there's always like a better model for a specific like problem. So I'm saying that I'm just demonstrating the lazy predict library because it's cool, because I like what it's doing. But yeah, I mean, these also provide like model names that I've never heard before, but it's a good starting point to choose a library. Yeah, but you can also improve the library. Oh, sorry, you can improve the model, right? With hyperparameter tuning, for example, or yeah, or you can improve the data too. So yeah, this is just a fun example of a library that you all can do. Okay, let's move on. The third topic on our agenda is TensorFlow. This is the documentation, the logo, and yeah, we're just gonna import TensorFlow. And here I want to talk about Keras. Keras is TensorFlow's high-level deep learning API, and it allows you to build, train, and evaluate and execute also all sorts of neural networks. Yeah, but at some point, like Keras was like integrated into different libraries or like projects, and TensorFlow also worked with different APIs. But at some point, they kind of decided to work together exclusively. So yeah, installing TensorFlow will automatically install Keras as well, and Keras will not work without TensorFlow installed. Cool. Hold on. Give me 1 second. Okay. Right now, I just want to demonstrate like a very simple neural network. Yeah. It's not that intimidating as you think. It just compared to like a machine learning model, like the architecture is different first, because with machine learning we have a model, but with deep learning we have neural networks. Does anyone know what neural networks look like? Okay, so okay, so originally, like a neural network, you would have like the input data, and then you have like a layer of neurons, and the like connections are the weights, and you would compute the output. However, with deep learning, there's not only one layer. There are like multiple layers, and they're called hidden layers. Yeah, and those are the layers that kind of perform computations. Yeah, so a deep learning network is very much more complicated than a simple neural network. But for our case, we're just gonna do a neural network with 2 hidden layers. So this is the code that we're gonna use. So first we install TensorFlow as TF. You can do a lot of, by the way, you can do a lot of data pre-processing with TensorFlow. So TensorFlow works similarly to NumPy, where you can, well, you get tensors, but in NumPy they're called NumPy arrays, but they're the same thing, kind of. And then so for example, if you have an image as an input, and the image is basically a combination of pixels. So a colored image would be like a 3-dimensional array. So it would have like 3 layers, like the reds, green, and blue. And yeah. And then for like processing of the data, you would try to convert it to a 1-dimensional array. Yeah, and you can do it with TensorFlow. So TensorFlow has a lot of capabilities for data pre-processing. And yeah, let's dive right into it. So for this particular neural network, we're going to use the fashion MNIST, like the fashion data. So the labels would be the items of like the clothes, basically. Yeah, and the dataset contains images representing fashion items. Yeah. So we load the data into this variable, and then we split it into, well, it's already split into the full training dataset and into the test datasets, right? What we're gonna do is we're gonna take the full training dataset and we're gonna split it into training and validation. And this is a technique that I learned in my data mining course. So you would need the validation dataset acts as a test dataset. So you would train your model on the training set, and then you would test it on the validation set. But for example, if your model was very bad somehow, or the data was like had some defect or like was not clean, whatever it was, well, now you cannot really reuse this data, right? You have to like change your model, but yeah, you still have the test set that wasn't used. So you kind of need the validation set to like test the model itself, if the model is good enough. If it's not, then you kind of tweak the model, and then you still have the test set. Yeah. Okay. So yeah, we're gonna do that, and since the dataset contains images, so it's pixels, right? We gotta, for simplicity, we gonna scale the pixel intensities down to like the range of between 0 and 1. So the maximum range would be 255, but now we're gonna pretend that the maximum range is like, wait, the maximum value is 1. Yeah, and those are the class names. So based on the image, or like on the like combination of pixels, we can differentiate between a t-shirt, trousers, dress, coat, sandals, shirts, sneakers, and so on. Yeah, and now we're gonna call this model called sequential, and it's the simplest kind of model, the simplest kind of Keras model for neural networks. Yeah, and it's composed of a single stack of layered connections sequentially. So it's still gonna be this, but it's gonna be like one layer only. Okay. Cool. Yeah, and what we do right now is we build the first layer, so the input layer. Let me just bring that up. So the red one, we need the input layer. We specify the shape, which is important. And then we add a flatten layer, and it basically converts each input image into a one-dimensional array. This you could have done with TensorFlow before that, but we're just gonna do it right there. Next, we add the two dense layers, which is the two hidden layers. So it's gonna be like those two yellow layers, basically. Yeah. Okay. And the first layer would have 300 neurons, and the second one, like the second hidden layer, would have 100 neurons, and both of them will use the ReLU activation function. And yeah, and then finally we add the output layer, which will only have 10 neurons. Okay. Nice. So we could write this code more compact, in a more compact way. So this is like the same code as this. Yeah, and then you can call the summary on the model, and we can see the layers. So here's the flatten, and here are the two hidden layers in the output layer. Yeah, those are the layers again. And there are also like the weights and the biases are parameters of a layer. So once again, the weights are those connections, basically. Yeah, and we can explore that more, but right now we don't really need it. What we need is we need to compile the model. So we already created the model. Now we should compile it because we want to specify like the loss function, which is it's like categorical cross entropy, and the optimizer. Don't worry about those parameters for now. You could change them later on. I also encourage you to play around with this code because now you have it in your Google Colab. Cool. And after we compile this model, what we do is we train it. So once again, we call the fit method on this model using xtrain, ytrain, and the epochs. So, and the validation data, of course. So this step is going to take a while because we specified 30 epochs. It's gonna, yeah, it's gonna go all over the 30 epochs, and it's gonna take some time. And each epoch has like those statistics. So it's like the accuracy on the training set and the accuracy on the validation set, and the loss also. And when we look at the last one, like 30 out of 30, we can see that the accuracy on the training set is slightly higher than the accuracy on the validation set, which means that the model is slightly overfitting. So what we could do, we could train it more. But for now it's okay. So yeah, for now it's good. And we can also visualize it. So as the number of epochs increases, the accuracy tends to increase, but not by a lot, right? And the you see the training accuracy and the validation accuracy, they kind of diverge. So yeah, this difference is like ideally there would be no difference, but it's kind of because the yeah, in this case the model overfits slightly. Okay, and good thing about neural networks, or good thing for like data scientists, you don't have to specify what each neuron does. Like it kind of figures out the connections and the neurons itself. You just need to specify like parameters and metrics. Yeah. And once again, we can evaluate using, we can call the evaluate method, and it's going to give us the loss and the accuracy. Then we're just going to save it. We can save the model if you like want to save the progress. That's perfectly fine. Yeah, and this is where I want to talk about transfer learning for a bit. So usually a model or like a neural network is never the end goal. So usually it like feeds into another model, or you know, like it's usually not the end step, like the final step. So let's say we already trained a model on a data set to perform one task, but now we need to build a model that kind of performs a similar task to the one that we already trained. So a key thing that we can do is we can use transfer learning So we can use it to reuse the layers of an existing model. This is especially useful if you don't have enough data set for the new model. So you can just reuse like the layers of the previous one. Yeah. And then you can, the tasks that both models perform are not identical, but they are similar. And this is why transfer learning is so useful. And you can also follow this link. So yeah, it takes you to like a playground in TensorFlow, and you can play around with the features, the neurons. We can add neurons, but yeah, I like to use 4. And we can add the output. Oh wait, no, this is the second hidden layer. This is the output. Okay. Yeah, and it's really fun. And now I want to talk about, like, we came to the end of our workshop, and I want to talk about what happens next, and just to conclude this event. Thank you all for staying, by the way. Yeah, and what you can do now is you can do your personal projects. Data science is about using data for insights. So when you're working with data, like machine learning is a useful tool. Like it can help you build a model and automate certain tasks, as we've seen. And overall, it's quite simple to integrate into any data project. So usually, we did not do this today, but before like building a model, you would decide on performance measures and assumptions given the problem before you do anything. Then you get the data and you do lots of exploratory data analysis, cleaning, and data sanity checks. Yeah, and then you're gonna do feature extraction, which is quite useful. So then you're gonna build the actual model, which doesn't take a lot of time. So you will spend most of your time before you even build the model. Then you evaluate the model and see if like it's acceptable. If not, you're gonna tweak the model by changing the hyperparameters and maybe even reducing the dimensionality of your data. Yeah, and then you just do model validation. And those are the resources that I used in this workshop, and I recommend everyone to use. So this book is found on O'Reilly, and it's free for Baruch students. And it's like the data science holy grail, because it contains a perfect combination of theory and hands-on exercises. So I would recommend this to anyone who wants to learn more about like data science, basically. Yeah, and to gain like more practice, if that's what you want, you can practice your knowledge on DataCamp again. Some CIS courses at Baruch offer unlimited access to DataCamp, so yeah, maybe that's how you can get unlimited access. And also Codecademy. Yeah, Codecademy offers great resources. And follow us too. All right, this concludes the workshop. Thank you all for coming. Yeah, I'm gonna post all the materials and the recording today. Cool. Yeah, thanks. Bye. Okay.
All right.
Yeah.
Yay.
Nice. All right. Thank you. Thank you. Thank you for coming to this workshop and for participating. All right. Yeah.
You can stop the recording now.
Yeah. I'm gonna end the session and the recording will be available. So
Perfect.